There's one other thing we can learn from delta A that is a very useful piece of information. So let's again consider delta A for a reversible process. So we can write delta A equals delta U minus T delta S. This is just based on the definition of delta A. But for a reversible process, we know that the reversible heat exchange is equal to TdS, or T delta S, I should say, if it's integrated. So we can say that delta A is equal to delta U minus the reversible heat exchange. But if we just look at the first law of thermodynamics, delta U for a reversible process, we would have W reversible plus Q reversible. That means that delta U minus Q reversible is equal to W reversible. So we can say that for a reversible process, delta A is equal to the reversible work. So, and again, I'll just reemphasize, this only applies at constant T and V. Right, so this is not generally true, but if we have a constant volume process, this is true. So the change in the Helmholtz energy is directly related to the maximum amount of work that can be done by the system. So, and that's if delta A is negative, this is the maximum, right? If we do the process reversibly, maximum, let me write a better M there, possible work that can be done by the system, since energy would be leaving the system. So that's a very useful thing to know, right? This gives you an upper limit on how much work you can get out of a particular type of process. Alternatively, if delta A is positive, now we would have to put energy into the system to get whatever process we're considering to happen, and this is the minimum amount of work that would be required to drive that process. So this is the minimum amount of work required. So this would have to be work done on the system, since it's positive, to drive the process. Now, the reason we have this maximum here and the minimum here is because this is assuming a reversible process. And if we have irreversible process, which is real life, we're going to have things like friction and other losses, heat losses that'll happen that wouldn't happen if we had a purely reversible process, which is basically impossible to achieve. The irreversibility of the process will, require, will sap some of the work, right? It'll use up some of the work if the system is doing work. Some of that work will not go just directly into whatever thing you're trying to drive with it. And if we're thinking about driving the process, right, putting energy into the system, some of that energy has to go to these non-ideal conditions, right, friction and other things like that, if we're thinking about a positive value here. So this is one other piece of information we can get for a constant temperature, constant volume process from the Helmholtz energy. So it doesn't just tell us spontaneity, it can also tell us a little bit about what's occurring and how much work we can either get out of the system or need to put into the system to make the process happen if it's not spontaneous.